Okay, hey guys, good evening to all of you. Uh, Hope you all are fine and safe at your homes. So, here we are going to cover the Floyd Warshall algorithm, which is one of the most important algorithms that is regarded for finding the shortest paths. So, there are many computer programming questions, and it actually varies across domains. Sometimes, in questions where the onus is towards finding permutations, towards expected values, or something else, there are many such complex combinatorics questions where this is just a small part of the question where we have to always keep pre-computed the shortest path between all possible pairs of vertices. So we are going to discuss this. Maybe we can wait for 1 or 2 minutes till we have some people joining. I hope I'm audible. I should be clearly audible, and yeah, we'll be starting soon. So, before we jump into Floyd Warshall, let's see what we are leaving aside us. So we have got our first algorithm for shortest path, that is BFS, breadth first search. Given any kind of graph, which may be undirected, which may be directed, there is no restriction on that. But all the edge weights are basically one. Whenever you have that all edge weights are one, you can use BFS. You can use BFS to cover all of them. All edge weights are the same, that is equal to 1. Then you might have covered the algorithm of Dijkstra. That also works with similar kind of notions. You say that it is basically a greedy kind of algorithm. And after that you have Bellman-Ford, which works with a DP approach. Bellman-Ford. And finally you have this particular variant, which is Floyd Warshall, which works rigorously different from all these algorithms. So you have Floyd Warshall, which is totally different, drastically different from all the previous algorithms. So if you have covered this algorithm at some point of time, then it is a bonus, else also it is not a problem, because this algorithm is quite independent of all the previous things. But amazingly, the task that it performs cannot be performed so well by the other algorithms. So we are going to see basically what are the tasks that it performs. It basically works on any kind of directed or undirected graph, and what it gives us is that for all the pairs I and j, it tells us the minimum path length from I to j. I'm sorry, from, just let me position it once, yeah, from I to j. So for all the vertices, it actually gives us the shortest paths. And the most important part is basically how this DP is performed. So when we think about how we can, compute all possible shortest paths, you can understand the naive idea about all these shortest paths is how many ways can we traverse from I to j. You can choose the first vertex in n minus 2 ways. You can choose a second vertex in n minus 3 ways maybe. You can choose the next vertex in n minus 4 ways, and so on up to the end. This is basically the number of permutations you can choose in order to get from I to j, and this will give you close to order n factorial permutations. These are the number of possibilities of the paths that you have from I to j. So whenever we talk about shortest path algorithms, it is some knowledge, suppose greedy intuitions, or it may be some sub problems, some kind of optimization that they work with, due to which they can bring it down to much lesser numbers. So Floyd Warshall is one such algorithm which gives us the shortest paths from all sources to all destinations. This is not something that Dijkstra, Bellman-Ford or BFS do. Floyd Warshall does this, and it does this in order n cube time. So in this session, our emphasis shall be on understanding how Floyd Warshall proceeds, what are the iterations it proceeds through, and why ultimately it prints the correct answer. That is what we'll understand. Okay, cool. So let us see. First, what we start with is, we say that make a matrix where you are going to store the result. So it is, maybe you can say this is the state 0. Okay, this is the first version of your answer which you are going to improve upon. So over here what you are going to do is store all these vertices which you want to treat as the source vertices. Okay, so these are all your source vertices 0 to n minus 1, and here you have the destination vertices up to n minus 1. Now you will say whatever you will find that the shortest paths, wherever you will find that the shortest, basically the I is equal to j. Suppose for 0 0 you have the I equal to j, you have for 1 equal to 1. So these are the values where I is equal to j. For all such positions we say that the shortest path is what? It is 0. The shortest path is unambiguously 0. There is no time taken, or there is no path that we require to traverse in order to travel from 2 to 2, from 3 to 3, something like that. And about, in our graph, suppose we have something like this. So between the vertex 1 and 2, suppose we have some edge of length 5. We say that between, from 1 to 2, suppose this is directed, or you can even do for undirected, from 1 to 2 you have a path of length 5. So whatever edges you have, you will say that first let us fill with those. Whatever edges we know, let us fill with them. So if it is an undirected graph, it will be the same from 2 to 1. So we can say from 2 to 1 also it will be 5. And similarly, wherever you have edges, you are going to fill them. Okay? And you are going to say that the rest of the values will be filling with infinity. What infinity denotes basically is that from this ith node, you cannot reach this jth node till now. Using one edge, you cannot reach. This is something that it tells. Now we'll walk through how we improve upon it. Over here, see, we are saying that the shortest path from 1 to 2 is going to be 5. It can be something better, it can be something like this. From here it can be 1, 2. So 1 plus 2, it can give us a better path, which is 2 plus 1, 3, right? From vertex 1 to vertex 2, we can get a better path. So the idea is that we will adaptively improve upon this. Okay? And now let me first of all ask you any questions up to here. Floyd Warshall is an algorithm which is one of my all-time favorites, and the reason it is one of my all-time favorites is because of the intuition, the process that it undergoes. So I would be most excited to deal with the analysis part. So up to here we are only doing the processing, we are understanding the basics. So any kind of problems are you facing till now, or any questions do you have, or is it clear? Is it good to proceed from here? Yeah, hi Suraj. Cool. So let us see how we really improve upon it. Next time, now I'll do this periodically. I'll show you how it is done, and then I'll again tell you the reason behind that, and this will happen alternately. In DP1, we basically say that we are going to use DP0 in order to form it. Hello Hassan. So we do something like this. We say from I to a certain j, we'll be assigning a value such that dpij, or basically this particular value ij, we are first of all going to see what value you already have for I to j. Over here, we are going to see what is the value that is created by that single edge. If there is no edge, then this will be infinity. If there is an edge, we will have that value. We will say, we'll consider a different case when you go from I to 1 to j. This is basically what we are doing in DP1. We will say, let us consider that you are going from, or suppose, okay, we have indexed it from 0 to n minus 1. You can consider that we have indexed it from 1 to n if you want, or maybe let us choose the first vertex, which is going to be 0. Okay, so we will choose the first vertex in order to travel from I to j, because the vertices are named from 0 to n minus 1. And we will say, how can we get this path? We can get this in this manner: dp of I0 from here, dp of I0 basically, so I0 is going to give me basically this value, plus dp of 0j, so 0j, whatever value I have over here, this is going to give me this value. So from here I'll get this value plus this value, and I can say that okay, by these two things, dp 0j, we can refer this maybe as like this, dp0, and we can write this as dp1. So we can say dp0 I comma 0 plus dp0 0 comma j is going to give us a possible solution how we can go from the ith vertex to the jth vertex by choosing to place the 0, the vertex 0 as the intermediary vertex, and we are going to use that over here. Clear? We are going to say that what value are we containing over here? dp1 at ith row and jth column is going to be the minimum value of dp0 at ij, that is what is possible. What is dpij? It is a central location of diagonal. Where are you referring to? Maybe over here. So it is basically, where did I mention? I think, okay, dp1. So it is basically ith row and jth column. Okay, that is what I am referring as dp1 ij. And I will say that first of all, let me fetch the value for this particular cell from my previous matrix, and let me try some other version which is I to 0, going from I to 0, dp0 going from I to 0, and then going from 0 to j. This is something that I'll be doing. Now let us step into the fact, what is my intention? My intention is something like this. When I say dpi, suppose in this kind of, for all I greater than equal to 1, when I say dpi, what I am indicating is find the shortest path among all pairs such that those paths contain only the first I nodes as intermediary nodes. So now observe this definition very clearly. What we are seeing is that, and I'm sorry for my handwriting, but I hope it is legible. So what we are saying is that, and at the ith state of this dp, we will say that from any particular vertex a to b, I'll be finding the shortest path such that whatever I'm using over here, all these will lie in my first I nodes. What are first I nodes? 0, 1, 2, 3, 4 up to I minus 1. They are the first I nodes. So now let us look around and see what we have done in dp0. In dp0 we have said that the first 0 nodes I am concerned about. First 0 nodes means none of the nodes. So there should not be any intermediary nodes. बीच में कोई nodes नहीं रहना चाहिए. That is what I decide. And according to that particular principle, what I have decided is सिर्फ edges को ले लो और इस ग्राफ में रख दो. Now what I have said is dp1 में हम क्या करेंगे? dp1 में हम सिर्फ पहला नोड अलाउ करेंगे बीच में रखने के लिए. रख भी सकते हो, नहीं भी रख सकते हो, that's totally up to you. But I am going to allow only the first node to be there inside. So from a vertex A, if you have to go to a vertex B, you can either choose to go alone or you can choose to go through one. तो इसके लिए मैंने एक easy ऐसा relation निकाला कि एक है कि 1 के बिना जो तुमने already store करके रखा है, whatever you have stored already, without 1 being taken, keep that same thing I to j. And if you want to take this one, that is the first vertex, which is actually 0. If you want to take the first vertex, then take in this manner, that I want to go from I to 0 and I want to go from 0 to j. Make sense? That after this we'll basically have dp1 of ij, where I am allowing the vertices to use the first node, which is 0, as the intermediary vertex. Make sense? Any requirement of an example? Do you want an example? Or does it make sense till now? Cool. So let us proceed. If you have any doubts, you can always ask me, okay? अब हम बोलेंगे कि हम dp2 फॉर्म करना चाहते हैं, dp2 ऑफ i to j, और इसके लिए हम क्या बोलेंगे? अगेन डू द सेम थिंग. dp2 ऑफ i to j के लिए हम बोलेंगे कि take the minimum. Please sir, example. Okay, so I'll take an example just after or maybe okay. ठीक है, इस एक्सप्लेनेशन को कंप्लीट करते हैं, फिर हम एग्जांपल लेके okay. So let us do this theoretical part first. We'll first complete this theoretical part and then we'll move on to the example. We'll illustrate it better through the example, right? So let us see. When I'm saying, just remember this definition that we are saying that dpi is going to tell me all the shortest paths among all the pairs such that the pairs contain only the first I nodes as intermediary nodes. Only the first I nodes can be as the intermediary nodes. I cannot have something like, suppose A occurs the best like this, A to 9 and 9 to B. I cannot find this path over this, inside this. I can only keep 0 as the intermediary node, or I may say that there has to be a direct edge from A to B. That is only what I am allowing. I will not allow this. So this is the first idea. And here also I say, when I am going to from A to B, this path will be considered in dpi if all the nodes lie between 0 to I minus 1. Okay. Now what I'll say? I will say that if you are allowing the second vertex, if you are allowing the second vertex to be there, the first option is that you don't use a second vertex for your distance measurement. If you don't use, you can say that this should be exactly equal to dp1 ij. Why? Because dp1 ij says that using only the first vertex in between, what are the paths you can form? Using at most the first vertex in between, what are the paths you can form? And you can say that with 2 we are only getting one extra option which we are not using. We are not using this second vertex. So we are going to say that this is one option. Another option is use whatever you had and take me to 2. Now I'm desperate to reach, the second vertex, which is 1. So the first vertex, actually this is how we have labeled it. The first vertex is 0, then we have 1, then we have 2, and then we have 3. So when I'm talking about the first vertex, it is 0. When I'm talking about second vertex, it is 1. When I'm talking about third vertex, it is 2. So what I'm saying is that take me first to the to the second vertex, which is 1. Then take me from there to j. This is one path which dp1 ij does not give me. Okay, and this is how I'll be forming. Gradually I'll be leading to the final step where I'll say you can take anything as the intermediary nodes. I can say I can form dp2 based on the values of dp1. I can say any ith step, or suppose any kth step I can choose based on the k minus 1th step, which is nothing but something like this: dp k minus 1 ij, comma dp k minus 1 I think this should be, yeah, this will be k minus 1 plus dp k minus 1 j. It looks something like this, and gradually we can say, we can always, thus by induction, we can always find out for all k. From k minus 1 we can find it out. Let us take an example to make the things clear, because I think it has become a lot hazy for all of you. Let us take an example now. Suppose we have something like this. I am forming a directed graph. Okay, so you have something like this: 1, 2, 3, 4. That's it. Let us choose something like this. Let us choose something like this. So you have 10 over here. Over here, suppose you have 3. Over here you have 2, and over here you have something like 5, something like 6, and maybe we can draw some reverse edge. We can draw something like this over here, and we can, yeah. So too many edges, it's becoming too many edges, it will become difficult to compute. Can we take unordered graphs? I think that would be better. Let us take unordered graphs. Okay, let us just forget this. Let us take an unordered graph. So it will be something like this: 0, 0, and you have something over here and something over here. So you have 3, you have something like 10, you will have something like 4, you'll have something like 4, you'll have something like 4 over here, and that's it. Okay. Hi everyone. So we are going to solve on this example. Let us see what is our DP0. Now these vertices are 1, 2, 3, 4. Now they are all 1 indexed. Now DP0 is going to tell me that I am not going to use any intermediary edges, and I want to know what are the shortest paths. I will use 1, 2, 3, 4 as the source nodes and 1, 2, 3, 4 as the destination nodes. From 1 to 1 the distance is 0, from 2 to 2 it is 0, from 3 to 3 it is 0, from 4 to 4 it is 0. We can say if you have to go from 1 to 2, there is a path which is of length 3. So we can use 3. There is an edge basically. From 1 to 4 we know there is an edge of length 4. So we will be placing 4. 1 to 3 we still don't have anything. So we will place infinity. Why? Because there is no direct edge from 1 to 3. Similarly from 2 we can say we have 3 with 1. So 3 over here. From 2 to 3 we have an edge of cost 4. So we will have 4 over here. And from 2 to 4 we have an edge of cost 10. Now from 3 I will say that in order to reach 1 I still don't know any method, so I am going to keep infinity. To reach 2 I know a path of length of cost 4, and to reach 4 from 3, where is 3? Over here. So we are going to take 4. Similarly from 4 we can say we are going to take 4, 10, 4, 4, 10, 4. So this is going to be my matrix initial. This is going to be my first matrix. What am I saying is simply that whatever the edges are giving me, let me mark all those things. Now you can see this edge is not going to give me the shortest path from 2 to 4. But still I'm adding it for the time being. Maybe at some other time it can give me a better result, but for the time being I'm adding it. Make sense? Okay. So up to here, what I'm defining is that only the first 0 nodes can be the intermediary nodes. So I'm allowing only direct edges over here. Only direct edges. And you can see how it is in compliance with the definition we used for DPI, that what values we are allowing. Now let us see how we are forming DP1. For DP1 we can say it becomes something like this. For DP1 I am saying that allow only the first node to act in between. So if you have to go from A to B, you can choose either A to B directly, or you can choose 1 as the intermediary node. So let us look at it, how it is doing it. So from 1 to 2 it says, what else can I use? I can use 1 in between. From 1 to 1 it is 0, from 1 to 2 it is 3. So 0 plus 3 again means the same thing, which is 3. So I'll tell over here it does not matter. It prints the same thing. 1 to 2 is going to be 3. But you can see that using 1 as the intermediary node, None of them can actually improve their paths except this 2 4. So let us look at this 2 4. What 2 4 is going to do? 2 4 is going to say that I want to see if I can improve by using 1 as my intermediary node. So 2 will say I want to go to 1 and I want to go from there to 4. So what we will do as a result of this is basically follow this. From 2 to 1 we are actually taking a cost of 3. From 1 to 4 we are taking a cost of 4. So we have got basically a total cost of 7. But from 2 to 4 we can see initial cost was 10. So we will say this is the time when we have got to improve it. So we will now improve it and this becomes 7. Makes sense? Similarly we can say from 4 to 2 we can again say we can use from 4 to 1 to 2. So over here we are actually allowing the first vertex, which is vertex 1, to act in between. And I'm saying that you can do this by adding these two things. So what are these two things? For going from 2 to 4, what I'm saying is you do something like this: dp0 2 to 1 plus dp0 1 to 4. Right? So you allowing this, we can say that now if 1 is the intermediary node between any two nodes, then I can have that over here. Great. So now let's see how it proceeds. We are going to do exactly the same thing always. So the next time also I'm going to say something like this, that if you want dp3 of ij, or dp, suppose dp2 of ij, I will say do one thing. From ij, either you will have only the first node or nothing, that is only up to the first I nodes, I minus 1 nodes, that is this 2 minus 1 nodes, or you are going to have somewhere 2. Okay, so you are saying that either we can have 2 or we cannot have 2. Basically there are two. What we are allowing over here in this matrix is we are allowing all the vertices from 1 to 2. That's it. So these are the two things. Now what can I say? That using 1 I know all the shortest paths, using 1 as the intermediary nodes. From I to j I can have something like this. I can have going from 1 to 2 to j. I can have something like this going from 2 to 1 to j. I can have something like this which can go from directly I to 2 to j. I can have something like this which can go directly to 1 to j. I want all these conditions to hold, and I also want this condition to hold. Does this make sense? If I say that the first two nodes, I'm considering the first two nodes can lie in between, then these are the possibilities to go from I to j. I can choose either 2 in between, or 1 in between, or nothing in between, or 1 then 2 and 2 then 1. Does this make sense? Or tell me, I will repeat slowly maybe. Does this part make sense? That if you have to target something like the first two nodes are allowed to stay in between, then these are the 5 possibilities. Does this make sense to all of you? You can write on the chat maybe. Okay, great. So now let us understand. dp1 and then any AB, this gave us 2 possibilities. What were those 2 possibilities? A to B and A to 1 to B. So now let us understand this particular path. Can we say that this was stored in my dp1 I comma 2? Can I say that this is the shortest path using only one vertex, the first vertex? This is the shortest path from I to 2. Can I say that this was stored in dp1 to 2? And then we can say that okay, this we can say this was also stored in dp1 of 2 to j, because they are not using any intermediary nodes other than 1. So I can say that this was stored in dp1 to 2 and this was stored in dp1 of 2 to j. Makes sense? Why? This came from dp0 of 2 to j. So I was saying that okay, whatever is the minimum you can form like this. Makes sense? So from here, what can we say? Can we say something like this? From 2 to j, we are going in this manner. So now our final path, if this is the shortest path, I'm going to find it from the summation of these two values. Basically the summation of these two values, 1 and 2 over here. Can I say that by adding these two values, I'm going to get the value of this particular path? This is the idea. Now suppose, on the contrary, you're looking just for I to 2 to j. If this is the shortest path, that means this has to be the shortest path for I to 2. Hence, this will be stored in dp1 of I to 2. And this will be stored in, this is again the shortest path for 2 to j. So this will be stored in dp1 of 2 to j. Okay. If suppose this is not the case, suppose rather 2 to I to j is a better path than 2 to j, or 2 to 1 to j. Basically, suppose 2 to 1 to j is a better path than 2 to I to j, then this cannot be the shortest path, right? Then this cannot be the shortest path. What are we talking about? Shortest paths where 1 and 2 are there in between. So if this is the shortest path among all these 5 possibilities, then this must be the shortest path from I to 2, and this must be the shortest path from 2 to j. So by adding these two values, I can find out. Similarly, let us consider I to 2 to 1 to j. If this is the shortest path, suppose like let this be the shortest path from I to j using only 1 and 2 in between. Okay, you can use only and at most 1 and 2 in between. So what can we say? That using only 1 in between, which was given by dp1, we can say that I to 2 is going to be the shortest path from dp1 of, we are going to get this from dp1 of I to 2, and this is going to be the shortest path from 2 to j, and we are also going to get this from dp1 of 2 to j. Why? Because intermediary nodes are only 1. So we can say that just by adding these two values, I'm going to always get this shortest path. Can we say this? So eventually what I am doing, in order to form the dp2, I'm using the second vertex as a bridge to connect the other two segments. Does it make sense? So this is actually the trick. Then if I say, so up to here, do you have any doubt? Now a question may arise in your mind that what happens if I to 1 to j, suppose what will happen if this is the best path, 2 to j, something like this. If this is the shortest path, then we can say that there is a negative kind of a cycle, right, which is leading to this. But for a moment, let's assume that there is no negative cycle. So if there is, like, if the shortest path from 2 to j is going to be through 1, and if the shortest path from I to 2 is also going to be through 1, then that is a problem that will arise only if there is a cycle at 1. Okay, so basically it's saying something like this. So you can go from I to 2, but you are going from 1 to 2. If all the edge, suppose all the edge weights are positive, and you have something like this, you are preferring this, and then you are saying that from here you can go to 1 once again, you'll go over here once again, and then you'll go to j. I can say if all the edge weights are positive, you should rather choose this path, go directly from I to 1 and 1 to j and finish the things. Why are you traveling in between with 2? So this kind of a case will never occur if the edge weights are positive or greater than or equal to 0. So up to here, can you see that all the other cases we have solved? Now suppose, now I want to show that suppose I is equal to suppose I to j, the shortest path is something like this. You have I to 4, 4 to 1, 1 to 3, 3 to 2, 2 to j. Suppose this is the shortest path, and I want to know how my dp recurrence is going to give me this path. So the first time, what can I say? dp0 will look something like this. dp0, I can say that dp0 I to 4 is going to be something like A, B, C, D, E, suppose. Fine. This is the shortest path from I to J. So what can I say? dp0 of I to 4 is going to be A. dp0 of 4 to 1 is going to be B. dp0 of 1 to 3 is going to be C. dp0 of 3 to 2 is going to be D. dp0 of 2 to j is going to be E. From here, the first thing that I'll do is I will say that from I to 1, okay, so now I'm allowed to use 1 as the intermediary vertex first. So I'll form dp1 and I will say use dp1 as the intermediary vertex. So using 1 as the intermediary vertex, whatever are possible, my algorithm is going to compute all of them in dp1. So in dp1, what will I say? I'm going to take this path into consideration. So now my dp1 of 4 to 3 becomes equals to b plus c. It becomes equals to b plus c. Make sense? Now I'll say that using dp2, find out what are the better paths you can form using 2 as the intermediary vertex, up to 2 vertices from 1 to 2. So whatever are possible up to 1, you can just copy down dp1, and whatever are possible with 2, utilize 2 over there. So what can we say? There are two things we can find from here. One is, in order to reach 3 to j, we are getting a good path. We are getting 3 to j, that is equal to d plus e. There is another good path. Okay, no, we have not yet found it. So this is the only good path. We are saying that in order to go from 3 to j, we can utilize this node in between. Now we can say, let's try utilizing node 3 as well. Now we'll utilize node 3. I'm sorry. Now we'll utilize node 3, dp3, and we will say dp3 helps in merging which ones? dp3 will help in merging 1 and 2. You can directly merge because you know that 1 to 3 is going to be C and 3 to 2 is going to be D. So dp of 1 to 2 is going to be something like C plus D. What else? Can we say that dp3 we can also merge 4 to 2. Why? Because we know that dp2 of 4 to 3 is going to be b plus c. We know this. 4 to 3 we know, and 3 to 2 we already know from here. And we are going to copy these values. 3 to 2 we haven't found a better thing after this. So we're going to copy this. So it becomes b plus c plus d. So we are actually having b plus c plus d. And then gradually what can we say? Using 3, this is the best we could do. You can try the rest, 1 to 3, but where will you go from 3? 3 to j. Well, this is interesting. You can now go from 1 to j as well. You can see dp of 3 from 1 to j. What is it going to be? It will be dp of 2 from 1 to 3 and dp of 2 from 3 to j. So 3 to j we know it is d plus c, and 1 to 3 it will be c. So we can directly say it is c plus d plus e. So we are having these as the possibilities. Now we can say that if we include this fourth vertex as a possibility, so what do we get? dp4 I to j can we get from here? From I to j we can say we can now use which vertex? We can use 4. We can go from I to 4 and we can go from 4 to j. So I to 4 I to 4 is A, and 4 to J, what do we have? Now this is another thing. Using this 3, one thing else you can do. Using this 3, you can also bind 4 to J. How? Because you already know how to reach from 4 to 3 and how to reach from 3 to J. You already know this how? You know this path from where? You know this path from dp2 of 4 to 3. And you know this path from dp2 of 3 to J. So you can say I can now add these values 4 to 3 and 3 to J. 4 to 3 is B plus C, and 3 to J, what is 3 to J? 3 to J is going to use 2 as the intermediary node. 3 to J is D plus E. So you'll have B plus C plus D plus E. So you'll have dp2, I think it was 4 to J. 4 to J is B plus C plus D plus E. Okay. Next, what can I say? Now when I want 4 as my intermediary vertex, that is my last intermediary vertex, what will I say? That from 4 I know how to reach the destination, because all these vertices are smaller than me and they have been visited, and I have utilized them to calculate my shortest paths that they can get me to. So it knows the shortest paths to J. I know the shortest path to 4. I can just add it. So it will be A plus B plus D plus B plus C plus D plus E. So it will basically A plus B plus C plus D plus E. It will be something like this: A plus B plus C plus D plus E. Make sense? So by this, what I actually proved is, if this is the shortest path, at some time or the other, I am going to get this shortest path. So it doesn't happen that when I do this for the ith vertex, I need to consider all the vertices once again from 1 to I. No, I just said that using I minus 1, you have already found whatever you could. Now use I in between and try to merge them. And we are successfully able to merge them for any kind of sequence. You can find this out. Does this make sense? This is not a very well-known thing. Like, for many people who apply the DP, it is not clear why we apply the DP. So I hope you have got some clarity. Any doubts up to here? So basically our recurrence will become something like this. dp of 0, let me take the darker one. dp of 0 is equal to dp of 0, suppose ij, equals to cost of edge I to j if eij exists in the edge set, and it will be infinity otherwise. Okay, this is my base case. Then what I'll be saying is that now dpij, if you know, sorry, dpk, if you know k minus 1 at 1, if you know k minus 1 state, you can find out for the k state as well in this manner. It will be the minimum of, now it is 1 indexed, all vertices are 1 indexed. So we will say utilize k minus 1 at knowledge I j and try to do better. How? K minus 1 I to k plus dp of k minus 1 k to j. This is actually the formulation, and we do this for all k greater than 0. So what do we see? From this 0, dp0, we'll be able to get dp1 from here, because dp1 calculates on the basis of dp0 values. Then from dp1, so on the basis of dp0 values, we can calculate all dp1 values from this equation. From dp1, again using this formula, we can calculate all dp2 values, then all dp3 values, and finally I will get all dpn values. Make sense? And this is what I require. Does it make sense? Right? So what can we say? This can be easily solved in a tabular manner. If we have different matrices, we can solve it, right? We can easily form different matrices. How many matrices will be made? So from dp0 to dpn, there are n plus 1 matrices, right? And what is the okay, so for all these values, what is the computation time? What is this calculation time? Can you see that this is order 1? Just you are fetching 2 or 3 values and you are doing some small computation on them. So for every cell, you are computing only once. How many cells are there? N square. So for every cell, you are doing order 1 computation and there are n square cells. So you can say this is basically going to be order n cube total computation. Make sense? This is the time complexity of Floyd Warshall. Now suppose you say that dp1 is equal to dp2. Can you terminate the process here? I'm sorry, this is actually the 5th class I'm taking today, so I'm a bit tired. So anyway, let me know if you have any problems, because I'm trying to give my energy, but it will actually become complete when I get the full reciprocation from you guys as well. Otherwise it will be speaking to a wall, right? So if dp2 is equal to dp3, what does this indicate? इससे क्या indicate होता है? क्या पता चलता है? What do we know from this? If dp2 is equal to dp3, which means all the values are same, what do we understand from this? That there is no shortest path. There is no such shortest path utilizing, so from any A to B, if you find all the shortest path using the first 2 vertices, and if you find all the shortest paths using the first 3 vertices, then none of them is improving. None of the values are improving. Right? So introducing the third vertex, you're not able to gain anything. So what do you think? Should we proceed further? Is computing dp4 going to be okay for us? What do you think? Is my chat box not getting updated, or is it some usual disease? Okay, so from dp2 and when we go to dp3, if we see that all the values are same, that automatically means that this third vertex is not immediately getting used. But we cannot say that the fourth vertex will not get used. It may happen, right? That from 1 to suppose 6 when I'm going, the better path is from 1 to 4 to 6. So here 3 cannot help me, but vertex 4 can definitely help me. So I cannot terminate it in between. If I see one dp set is exactly the same as next dp set, I cannot use that to terminate in between. So it cannot be terminated in between. It will be strictly order n cube. Okay? Great. Thanks Ankitesh, and please keep on responding. Okay? Because इससे पता चलता है कि किस में हम कैसा time दे सकते हैं. We actually understand how we can divide the time. These are the things that I'll be analyzing after this. Do we need separate tables? Separate tables for dp0, dp1, dp2 up to dpn, or can we reuse the same table? Can I reuse dp0 to store dp1? That I'll be using all dp1 values. The moment, like while I'll be solving dp1, I'll be just overwriting on dp0. Can I overwrite on the same matrix? Okay, thanks Umang. Hope you understood something. This one we'll be discussing, and then the next thing that we can discuss it how to, if you want I can discuss the coding implementation for all of you, how we can code it. We can discuss the coding implementation after this. But after this comes the most important thing, which is how to retrace the path, how to find the paths. How to find the paths. That is from A to B, if this is the from I to J, if this is the path, then how can I retrace this path? How can I find out that later on I want to find not only the shortest path length, but I want actually the path. So we want to, like, I would tell you that try to think on this. We can discuss this. And the last thing that I can discuss is, what about negative cycles? What about negative cycles? Can we find this? Let's think about it. So while you think about this, and you can tell me which one you want, because if you want everything in a super fast manner, you can ask me, or you can choose which one you want. These are the 4 things that I usually cover in Floyd Warshall sessions. But usually when it is interactive, it becomes much faster and much smoother. But anyway, whatever is comfortable for all of you, it's not an issue. Right. So this is something that I would like to cover in these 1 or 2 minutes before we move on to the topic once again. So these are the batches. Okay, first one Abhinav says. So I'm coming back to it. So these are the batches which are currently being offered at Unacademy. I am offering this course. This is a 2-month master course on advanced programming topics, Mahayodha. This is Eklavya 2.0. This is for beginners, but this is of 8 months. So it will take you from beginner to expert level. Then you have Brahmastra 2.0, which is for college or off-campus placements. All have started on 6th of July. You will get a structured learning path, and if you take a subscription for a certain period, you will get access to all the batches and courses. Okay, you will get best in Coders of India's educators. Then in this Mahayodha batch, which this is the part which we have completed today, week 1 to 2. The rest are to be proceeded. So I am taking this batch currently. You have advanced mathematics, then you have got advanced dynamic programming, then you have got segment trees and problem solving on that. You'll have advanced concepts of graph theory and mixed problem solving. Then you have this batch structure for Eklavya, where you start with the programming fundamentals, then the intermediate topics, sorting and searching and stacks, queues, all those things, and then additional concepts for moving from one language to another, Java to C++ maybe. I'm sorry. So you have greedy algorithms after that, then you have again the expert level topics from week 21, square root decomposition, number theory, not expert level, advanced level. Then you have recursion and dynamic programming and graph algorithm with extensive problem solving. Then you have Brahmastra 2.0, where only the topics pertinent to placements are covered. You have preparatory course, basic fundamentals, then maths and puzzles, then sorting and searching, bit manipulation and bit tracking, and basic data structures. You have all these string algorithms. You might have heard the names: KMP algorithm, Z algorithm, manager algorithm, Rabin-Karp, all those things. Also trie-based things. So you have advanced dynamic programming after that, and graph algorithms. Interview problems asked in FANG or top product-based companies is going to be covered in the last 2 weeks. And these are your educators. This is actually the old list. And the list has been revised. You have live interactive classes, you have practice relevant problems and doubt support on Discord. The TAs assist you there. And these are the payment schemes. For 1 month you need to pay 6,000. For 12 months you need to pay 33,000. And for any price, you will get 10% off on the referral. If you use my referral code Saptarshi 1729, you'll get 10% off on top of all these discounted rates. Okay. So this is not the price for one course or for a particular educator or something. If you pay this for that particular period, you can observe everything. That is common. Okay. So let's come back. Any questions if you have, you can ask me. Yes, let's come back. Do we need separate? Okay, I'll start from the first one. Do we need separate tables for DP0, DP1, DP2? What different will we get? What will we get if we don't use the different DP tables? If we overwrite in the same table, what problem can arise? So I can face this kind of a situation that when I am filling it for I to J, it can happen that I'm using something like I to k to j. Okay, so I'm using something like I to k, this value, plus k to j, this value, and it might happen that these values have got updated, right? So when I'm referring to these values, what do I want? I want them to be of dp k minus 1, right? I want them to be of dp k minus 1, but in turn they are of the recent dp. It might happen that they have been overwritten. I've got the new value. Think about the possibility. Is it possible that from k to j when you're going, from k to j when you're going, k lies in between? Is that possible? Supposing that all the edge weights, suppose all the edge weights are basically greater than equal to 0, is this possible? We can directly say, right, go from k to j. Why are you going in such a long manner? If this is path p2, follow exactly p2. Why are you proceeding through an additional path p1 to travel to the same vertex k? So in this iteration समझने की कोशिश कीजिए. इस iteration में अगर कुछ ऐसा हो गया जो हम लेना नहीं चाहते, तो मैक्सिमम क्या हो पाएगा? वो ये हो पाएगा किसी को, like if anybody has any problem with Hindi, then let me know. If anybody has any problem with Hindi, please let me know. Else I'll continue with both the languages so that it becomes clear to you, because language is not important to you. What I convey is important to you. So the important thing is कि अगर मैं ऐसा सोचूं कि मुझे पिछले मैट्रिक्स से छापना था वो वैल्यूज, और मैं इस मैट्रिक्स से छाप रहा हूँ, डिफरेंस कहाँ पे आ सकता है? अगर कोई एक पर्टिकुलर वैल्यू चेंज हो गया इस इटरेशन में, तभी डिफरेंस आ सकता है. इस इटरेशन में कौन कौन से वैल्यूज चेंज हो रहे हैं? जो शॉर्टेस्ट पाथ k को बीच में यूज करके इंप्रूव हो रहे हैं वही चेंज हो रहे हैं. सो इफ k को यूज करके कोई भी वैल्यू चेंज हो रहे हैं, k को यूज करके कोई भी वैल्यू बेटर हो रहे हैं, कैन वी से कि इसके टर्मिनल्स में k नहीं हो सकते? k टू j या फिर समथिंग लाइक i टू k ऐसा कुछ नहीं हो सकता है. वाई? बिकॉज k ऐसा चीज रिपीट नहीं होना चाहिए इफ ऑल द कॉस्ट्स आर पॉजिटिव और ग्रेटर देन इक्वल टू 0. और तो कोई केस नहीं आता है. आर यू एबल टू गेट इट? कि ये पार्ट हमारा चेंज क्यों नहीं होगा? ये पार्ट जो कि kth कॉलम में है, ith रो kth कॉलम, व्हाई विल दिस पार्ट नॉट बी चेंज्ड? Because in order to reach something to k, the intermediary nodes should not contain k, right? So these values won't be changed. ये values change नहीं होंगे. ये values positive ऐसे cases के लिए change नहीं हो सकते हैं. So we can directly say कि we can safely use these values. हमारे ये values kth iteration में change नहीं होंगे. जहाँ पे like k को खुद पहुँचना है वो चीज़ change नहीं होगा. हम कह रहे हैं k को use करो बीच में. So definitely I to k, इसके बीच में k नहीं रहेगा. k is not going to be in between this. So definitely मुझे क्या मिलेगा? अगर ये अभी dp k है, so dp k will be equal to dp k plus k minus 1 for this particular value. ये अभी dp k है, मुझे पता है कि I have not taken care enough. I have not taken enough care to separate them. But I know that for this value this will be equal. Why? Because I और k के बीच में k आके कुछ महान काम नहीं कर पाएगा. Similarly k to j, k बीच में आके कुछ भी नहीं कर पाएगा. So over here also it is unnecessary. And hence I know that these are two correct values. I am not going to get any wrong estimation by using the same table. Does it make sense? Negative cycle होगा तो that is a very different thing. But negative cycle नहीं होगा तो कभी नहीं. Like negative edges भी हो सकते हैं. But अगर ऐसा कभी नहीं हो कि आप k से घूम के आप k में गए और ये अगर नेगेटिव साइकिल नहीं है, तब कोई दिक्कत नहीं है. Like तब भी आप प्रूव कर सकते हैं कि ये ग्रेटर देन इक्वल टू 0 होगा. So this is like totally useless to use this kind of a path. Just forget this path और इसके बाद तुम्हारा जो भी j है डायरेक्टली वहाँ पे खींच के लगा दो. Make sense? So the only thing is negative cycle should not be there. कि k से हम k में ही जा रहे हैं और नेगेटिव होता चला गया. नेगेटिव साइकिल होगा तो उसको अलग तरीके से डील करेंगे. That is point 4. So is it clear why we are not using separate tables? Hope so. So we do not need separate tables. The answer is no and the proof has been done below. अब कौन सा जानना है तीनों में? Ankitesh has said the last one. What about the others? I hope you all are understanding. समझ में आ रहा होगा. ग्रेट, विच वन? ठीक है, नेगेटिव साइकिल का ही देख लेते हैं। अगर नेगेटिव साइकिल फॉलो करेंगे तो कुछ ऐसा हो जाएगा कि जब हम बोलेंगे डीपी हाउ टू हैंडल नेगेटिव साइकिल्स, तो वही सबका लाइक मेजॉरिटी ओपिनियन है, उसी को करते हैं। तो एक पर्टिकुलर डीपी आई जे क्या हो जाएगा जब आप यही ऑपरेशन करेंगे? तो ये क्या हो जाएगा? सपोज यू आर डीलिंग सो सपोज के पर आपका एक नेगेटिव साइकिल, ये घूम के आपका के में आता है, ठीक है, ये घूम के आपका बेसिकली के में आता है और ये नेगेटिव है, और ये बीच में जो भी लाई करते हैं बेसिकली ये सारे के से कम है। ऐसे हम साइकिल बना सकते हो अगर हम आप रैंडमली अगर बनाए 4 देन 6 देन 9 देन बेसिकली दिस, सो वी कैन से ये हमारा 9 है जो कि पूरा घूम के आता है अपने से छोटे वर्टिसेस देखते हुए और नेगेटिव हो जाता है सपोज, सो वी हैव 4 ओवर हियर, वी हैव -7 ओवर हियर, वी हैव 3 एंड ओवर हियर वी हैव -2, so this is a negative cycle, right? So we can say that कहीं ना कहीं जहाँ भी नेगेटिव एज नेगेटिव साइकिल फॉर्म करेगा, हम ये बोल सकते हैं कि उस नेगेटिव साइकिल में कोई ना कोई रहेगा जो सबसे बड़ा एलिमेंट होगा, हम उसको चूज कर रहे हैं एज के, ठीक है, हम उसको चूज कर रहे हैं एज के। तो अब हमें क्या पता है कि डीपी आफ्टर द kth स्टेप, after the kth step or maybe after which step, suppose after the 6th step, in this case इस केस को लेते हैं 6th स्टेप में, 6 को जब इंक्लूड करेंगे हम क्या कहेंगे, फ्रॉम 9 to 9 इन दिस स्टेप क्या हो जाएगा, समथिंग लाइक दिस। ये DP5 को भी देखेगा, DP5 क्या क्या कर सकता है, फ्रॉम 9 to 9 अप टू 5 यूज करके हमें कोई साइकिल नहीं मिल रहा इधर, okay, but it will do something like comma dp5 from 9 to 6 plus dp5 6 to 9 and what can we say, ये वैल्यू हमारे पास स्टोर्ड है 9 to 6, 5 तक नोड्स यूज करके हम क्या क्या फॉर्म कर रहे हैं, 4 - 7 3, so it becomes 0 and what is the shortest path from 6 to 9? It is -2. So shall we get -2? So can we guarantee कि कहीं ना कहीं हमारा एक नेगेटिव एलिमेंट आ ही जाएगा? Can we guarantee this? कि हम जब ये पूरा DP फॉर्म करेंगे तब कहीं ना कहीं हमारा नेगेटिव एलिमेंट आ ही जाएगा, because we are looking at all possibilities. कोई डाउट्स है तो पूछना। आई कैन समराइज इट अ बिट। व्हाट आई डिड ओवर हियर इज कि जब भी कोई नेगेटिव साइकिल रहेगा उनमें सबसे बड़े एलिमेंट को सोचते हैं यहाँ पे, तो या ओके फाइन, इट्स ग्रेट। So we can actually say that using the next greatest element as the intermediary node, we can get -2 over here. और आप ये भी चेक कर सकते हैं कि by the time we reach DP9, जब हम DP9 रीच कर जाएंगे तब ये सारे के सारे जीरो लाइक नेगेटिव हो जाएंगे। इन सब के पास DP फाइनल जो DP होगा 5 to 5 ये भी जीरो हो जाएगा, ये भी जीरो हो जाएगा, ये भी जीरो हो जाएगा। कैसे? हम ये चेक करेंगे 5 to 9 हम कितने में जा सकते हैं, 9 to 5 हम कितने में जा सकते हैं, ऐड करेंगे तो वापस नेगेटिव मिल जाएगा। तो ये जो चीज़ होगा हम सीधे सीधे कह सकते हैं कि बाय द एंड ऑफ ऑल इटरेशंस जहाँ भी नेगेटिव साइकिल फॉर्म हो रहा है, जो भी नेगेटिव साइकिल में है, उनमें से जो भी नेगेटिव साइकिल के अंदर बिलोंग कर रहे हैं उस साइकिल वाले जो भी होंगे के से के तक हमें सारा नेगेटिव मिलेगा, दे विल ऑल बी लेस देन जीरो, राइट? ये हमेशा होगा। बट ऐसा नहीं हो सकता, लाइक इससे ऐसा कुछ हो सकता है कि आपको 100 मिला यहाँ पर और इधर घूमते घूमते आपको बहुत कुछ मिला है, दिस इज अ नेगेटिव साइकिल, सपोज ऐसा आपको कुछ मिला है एंड इधर आपको मिला है 1 सेकेंड 100। यहाँ पर कुछ छोटे छोटे चीज़ें हैं बट द ओनली थिंग इज दैट इज नेगेटिव, -1 0 0 0, so you have a negative cycle, a small negative cycle. Okay, I'll cover the rest in English. So you can see that it is a small negative cycle. So you can say from I to j, I am not going to have dp of ij. I'm not going to have dp of ij less than 0. This is not going to happen. Rather, we will have what will we see? It may be 100 minus 1 plus 100, or maybe slightly less than that. But on the other hand, we can say that all of these nodes have a negative cycle of size 1, size minus 1 at least, cost minus 1 at least, minus 1, or maybe even more negative. अगर बार बार computation करें, if we recompute, then it can become even lesser, because we are computing minimum at every stage. So what can we say from here? That this is not going to hold, but we can say whatever, there must be some value where it is reaching, where we can reach from I, where there is a negative cycle basically. So I can say for this k, I can say that dp k is going to be less than 0. So what can I say? From here I can basically say that take all those k's which have negative cycles or which are involved in negative cycles, take all of them. You will find all of them by this kind of mechanism. Read the table and get all the values. Then you will say, find all the vertices which are reachable to these values. Find all those I, and find all the j's which are reachable from these values. So find all the i's from where these values are reachable, and from these nodes find all the j's which are reachable. For all those cases, we can say that dpij is undefined. Why undefined? Because it can proceed up to minus infinity. So there is nothing defined, right? So we have got the elements which are involved in a negative cycle. We will definitely get them. For them also, we need to finally say that they are undefined. And for some other values, we need to say that to all these values to all these vertices which are lying inside negative cycles, which are the vertices from where I can reach these values, and which are the vertices to where I can proceed from these values. For all those pairs, for all these pairs of I with these pairs of j, I can say that suppose take a k, suppose take a certain k, whatever I1, I2, I3 I can always lead to this particular k, and whatever j1, j2 come out of this, I can say that for all these I1, J1, I1, J2, I2, J1, I2, J3, I3, J2, they are all such pairs. This is the important thing. So for a certain K, you are saying that find out all the things that are leading to it, and find out all the things that it is leading to. So whatever I is there, whatever J is there, for that this is going to hold. Make sense? Great. So yeah, how to find the paths? Basically, at every point of time, how to find the paths? Basically, you can always try. Like today, we have already passed the time, but we can always try. Storing that when we are forming a value, what is that intermediate node we are using? We can always form that. So what do we say whenever we are using an intermediate node? Definitely, suppose it is dpij. Okay, it is dpij. Whenever I say that with this dpij, I'm going to store that which k is actually joining them. Now I'm going to say that in our solution we'll be placing k, and the left part will be forming using what? Using the values from dp ik, and the right part I'll be forming from using the values of dp kj. So everywhere, in every state, I'm storing that for this particular shortest path, what is the best transition I'm making. That is what I'm storing. So whenever I'm storing this, using those values, we can recover it. You can try coding it. I've said it in very short, but up to here, if you have any doubts regarding any part, you can ask me. I'll stay for 1 or 2 minutes. Any doubt, you can ask me. Okay, before finishing, just a small comment that let us know whatever. Yeah, I'm on code forces. I am on code forces. I have been a master in code forces, but okay, recently some degradation has taken place. I'm trying to restore on them. I am myself a 6-star rated coder at CodeChef, a master at Code Forces. I have been to the ICPC regionals in 2019, and I'm going to join Google quite soon. That's about myself. Okay? Thanks that you all liked it. You can let us know about your experiences, about what other things that you want to learn. मैं उतना comments नहीं देखता हूँ, but maybe someone will convey to me, and you can always let us know about your feedbacks. Okay. Cool then. Thanks, Umang. And thanks to everyone. Take care. Good luck with all your endeavor. Stay safe. And bye. Take care. Bye.